Alright, so in this video I'm gonna be explaining this new paper recent paper 2021, 4 years ago, but it's still very important because it talks about graph kernels, and it's a survey of all kinds of the kernels. So they have attracted a lot of attention during the last decade and have evolved into a rapidly developing branch of learning and structured data. During the past 20 years, the considerable research activity that occurred in the field resulted in the development of dozens of graph kernels, each focusing on specific structural properties of graph. Graph kernels have proven successful in a wide range of domains, ranging from social networks to bioinformatics. The goal of this survey is to provide a unifying view of the literature on graph kernels. So we present a comprehensive overview of a wide range of graph kernels. We perform an experimental evaluation of several of those kernels on publicly available datasets and provide a comprehensive study. So you see the feature space and map defined by graph kernels. Any kernel on a space of graphs can be represented as an inner product after graphs are mapped into the Hilbert space. Because now, if you map to the Hilbert space, everything is easy to understand how to compare them, where are they, how they are clustered. You can understand it very easy, like any other modality. So you see this vertex histogram kernel is just one of them. Another one is edge histogram kernel. So this is taxonomy of graph kernels. As you see, some of them are explicit computation, some of them are node attributed graphs, some of them are convolution. For example, WL sub 3 is an explicit computation, but it also has intersection with node labeled graphs. So you can see how you can categorize different kinds of graph kernels, so that based on your research question, you can choose the appropriate graph kernels. So you see here two graphs and their dot product. So we have seen this dot product in the past 5 videos, that we can create a graph kernel on this using this dot product, using this product of graphs. And this is called geometric random walk kernel. So we have two graphs, and then this adjacency is the adjacency of the product graph. So for any two graphs, you can write it like this. But the direct product computation of geometric random walk kernel is computationally expensive. So it limits the applicability. That's why people use other kernels that are not very accurate, but still doesn't have this problem of computational complexity. For example, sub 3 kernel, this sub 3 kernel, or cyclic pattern kernel. This is a cyclic pattern kernel. So if we have two graphs, and then these are the sets of cyclic patterns and 3 patterns of 2 graphs, then the cyclic pattern kernel is defined like this. So we have this C, where C is cyclic pattern, but T, it means 3 pattern. Because we have 2 graphs, G and G prime, we do intersection and then add the cardinality of these calculations. Also, shortest path kernel is also very interesting. This shortest path kernel. So each triple is a feature and corresponds to, for example, label of source vertex, label of sink vertex, shortest path length between the two vertices. And then we can define shortest path kernel between any two graph. Oh, this graph-led kernel, there is a library you can calculate it very easily. There's pros and cons, because you know there are two kinds of graph-led that I care. Kernels that I care. One of them is graph-led kernel. So graph-led. So I've written a paper in Medium that saying what is the pros and cons of graph-led versus WL kernel. So it's a long history, but if you compare them, you understand that we still need to define a new kind of graph kernel, which has pros of both of these. So for example, graph-led is just a dot product of two vector that you create, you count, it's based on counting. And then here it's a neighborhood subgraph pairwise distance kernel. Also Lowas kernel, you know, Lowas was a great mathematician, and he didn't work on machine learning, just pure graph theory, pure spectral graph theory. But some people draw inspiration from his work and then invented this. Of course, this one is still a theorem that Lowas has proved, but this is how we define the Lowas kernel. So the Lowas kernel is defined like this. Also support vector machine V kernel, which is related to Lowas V kernel.